Okay. We so- we talk about Cauchy's integral theorem, as well as Cauchy's integral formula for example, for convex open set, and also for simply connected domains. All right. So they are basically we call local Cauchy theorems. So today, I would like to present the global Cauchy theorems, which apply to arbitrary open set in the complex plane. Okay. All right. So so first of all, I will introduce several new concepts. So we will denote a formal sum. Okay. Of passes. Okay. Gamma. One plus that, two plus that, plus of m passes, gamma 1, gamma 2, as, all right? So we put a dot above the plus sign to denote that it's just a formal sum. Okay. As okay, as a chain, okay, consistent of m passes. Okay. So a formal sum of m passes is actually is called a chain, all right, of m passes here. Right? And we define the reason why we give a chain is because to define the following things. The line integral, right, of a complex function f of z, okay, along a chain gamma, okay, as okay. So the definition is just it's just the sum of the just the sum of the line integral of the same complex function along the ice-path for all I from 1 to n. Okay. If each non-integral exists. Okay. All All right, so you can see that our target is to compute such a sum, right? Okay, so we just denote, so we create an object called chain of m passes, okay, as gamma, and we define this sum actually as the line integral of a complex function along the chain, okay? Now, if each path gamma I, right, is a closed path, right, this is quite often appeared in our discussion in complex analysis, then gamma is called, right, a cycle. Okay, so a chain becomes to a cycle. So a cycle is a special kind of chain, such that the constituent paths are all closed paths. Okay. Now, a chain, okay, may be represented as a sum of passes in many ways. Okay, so to say that, because our main purpose to define a chain is because to find the sum of these line integrals, right? This is our main purpose. So to say that a chain gamma 1, gamma 2, gamma n is equal to another chain. Okay, so this chain consists of m passes, but this chain consists of m passes. Okay, and this passes may be different from those passes. Okay, but we say that these two chains are equal, right? Equal. We mean, right? We mean that we mean simply that if we evaluate the line integral, right, for every gamma I, and the sum over OI will be equal to delta J, the sum of all the line integrals over passes delta J. Okay, so if these two sums are equal, then we say that the corresponding two chains are equal. Okay. All right. So any questions? This is just definitions. Okay. Okay. And this is for every, of course, for every f that is continuous. Okay. On the union of the images of all these passes Okay, because if f is continuous on this state, then all non-integrals appears on both sides will exist, right? And so we can evaluate the sum on both sides, and if they are equal for every such f, then these two chains are said to be equal. Okay, so for our purpose, we define gamma star to be the union of the images of all passes which form this chain. Okay. Now, if gamma is a cycle, which means that gamma is the sum of cross passes. Okay, so if gamma is a cycle and alpha and we say Z0 is not in gamma star. Okay, right? So Z0 is not in this union, right? The index, now we define the index of Z0 with respect to gamma, the cycle gamma, is defined as, okay, so we define the index gamma Z0 to be the 2 pi I and the non-integral dz. Okay, so now from the definition of the integral over a cycle, so that it is clear that the index of Z0 with respect to a cycle gamma is equal to the sum of the index of Z0, right, with respect to gamma I for I from 1 to n. Okay, so this is from the definition there. So we know that. Okay, and we also the minus gamma, right? Because we use minus to denote the minus gamma 1 plus minus gamma 2 plus plus minus gamma n, right? So which means that minus gamma is the chain, right? Which is the sum of the opposite of every constituent path R sub I. Okay, so as we know, minus gamma I is basically the same path but with opposite direction, right? So the orientation is just in the opposite direction. Okay, so with this, then we know minus gamma fz dz becomes minus, right? So you can see that. So if the orientation, right, of this passes is in the opposite direction, right, then this line integral over minus gamma would be equal to the minus of the line integral over gamma. Okay, so that is immediate. Okay. Okay, and in particular, all right, the index of this 0, all right, with respect to minus gamma is equal to the minus of the index of gamma, this is 0. Okay, for all cycle gamma, and Z0 is not in gamma star. Okay? All right. So this is what we know. Now, chains can be added, and so now we can define some edge break operation called addition. Okay, subtracted, right? In the obvious way. Okay, so for example, gamma 1 plus gamma 2, right? So formal sum, right? Gamma 1 plus gamma 2, okay, Fz dz, okay, right, is equal to, right? So the line integral along the sum of two chains, all right, is the sum of the line integrals along gamma 1 and along gamma 2. So this is very interesting. And similarly, minus gamma 2, this is the subtraction, right? So now you so this is equal to minus, okay, so we have that, okay, and for all f, all right, for all f, all right, which is continuous, all right, on gamma 1 star union gamma 2 star. Okay, you understand? Now we are able to state the global Cauchy's theorem. All right, so now omega, an arbitrary open set in the complex plane, right? So omega can be any open set. And F is analytical, okay, on the omega, i.e. F is in the vector space of all holomorphic functions, all right, on omega. All right. Now, if gamma is a cycle, right, in omega. A cycle in omega means what? Means that gamma star is contained in omega, okay? So gamma is a cycle in omega such that okay, that satisfies the index of Z0 is 0 for all Z0 not in omega. Okay. So suppose that we have a cycle, okay, in the open state, and we know that the index of point Z0 with respect to gamma is 0 for every point not in omega. Okay, so this is the premises. Okay, if then we have Fz and times the index of gamma z is equal to 1 over 2 pi I and the gamma f eta minus z and d eta for all z in omega, but for all z is in omega, but not on the image of gamma. Okay, so you can see this is just the Cauchy integral formula, right? This is the Cauchy integral formula. But this formula is good for any open set. So omega is be open set, and it's good for any cycle, okay, in omega. Okay, but the requirement is that for every point not in the open set omega, okay, means the outside of the open set, right? The index of Z0 should be 0 with respect to this cycle. Okay, so we have to check this condition. If this is true, then we have the Cauchy's integral formula. Yeah. Okay? This is the first. And this second consequence is that if gamma 1 and gamma 2 are cycles, right, in omega, all right, such that the index of Z0 with respect to gamma 1 is equal to the index of Z0 with respect to gamma 2 for all Z0 not in omega. Okay, not in omega. Then we have that the line integral, all right, over C1 is equal to the line integral over C2. Okay. Okay, so this is basically is the Cauchy integral theorem. Okay, basically, it's Cauchy integral theorem. Why? Why do we say so? This is equivalent to saying that the index of gamma 1 minus the index, right, of z0 is 0. Okay, with respect to this difference. So if the index of z0 with respect to this difference, the difference of gamma 1 and gamma 2 equal to 0, right, for all points z0 not in omega, then this is equivalent to saying that the integral right. So from here you can see this is the Cauchy integral theorem. Okay, so this global Cauchy theorem is a combination of the Cauchy integral theorem as well as Cauchy's integral formula. Okay, right. But they are good. That the conditions, the consequence. Then before that, we have to check, right, the condition, right, for all the points not in the open state. Okay. This condition, and all this condition. Okay. Okay. And I will write up a complete proof in a revised version of chapter 14. Okay. So, and such the proof will need the theorem, the Morella's theorem that we mentioned on Tuesday. Okay. Okay. So this is so in many situations we need the global Cauchy theorem, right, to apply to have the guarantee, okay, of many important consequences. Okay. So do you have any questions? All right. So if no questions, then so I'll move to chapter 15, and the first section has been assigned in last recommended exercise as a self-study material. Okay, so so I will start it with section 15.2. Okay, so about power series and Taylor series. Okay. All right. So this section is about power series. Right. Now, given a complex number, Z0, and a sequence, right, Cn, and from 0 to infinity of complex numbers. Okay, the infinite series of power functions. Okay, summation n from 0 to infinity Cn z minus 0 to the nth power. All right, so each term is just a power of z sub z0 multiplied with a coefficient. So, and such an infinite series of power function is called a power series, because it is an infinite series of power functions. So that's why it's called power series. All right, and about the point z equal to z0. Okay, so where z0 is called the center, right? And the Cn called the coefficient. Okay, of the power series. Okay. So from this definition, we see a power series can be completely specified by its center, z0, and its coefficient, c sub n. Okay, so basically, if you give a complex number, z0, and a sequence of complex numbers here, then you will define a power series uniquely. Okay. And there is a convention. So without explicitly mentioning the center, a power series will be assumed, to have 0 as its center. Okay, so when we talk about a power series without mentioning its center, we just means that its center is 0. Okay, it's 0. So that is the convention we will use in the rest of the semester. Okay. Now, and we know that this is power series may converge or diverge, depends on z. Okay. For example, if z equal to z0, so if z is selected as the center, then this power series must converge because its value is 0. Okay, so that but if z is selected maybe far away from this 0, it's possible that this power series will diverge. And we have studied the convergent property as well as divergent property in the first section, right? For a sequence. Okay, so there are quite a few tests, right? You have learned, for example, the root tests, right? And the several versions of ratio tests, okay, for us. And I believe that you have learned some tests from your calculus class already. Okay, so that's why I ask you to self-study the first section, even though actually I wrote a lot, all right, maybe beyond the material you learned from calculus course, but But I believe you already studied that section already. Okay. Now, so all right. So the first theorem. Okay. The first theorem gives the convergence property of a power series. So given a power series, okay, summation Cn z minus 0 as power. Now we let alpha to be the lim sup. Okay. Of the nth root of the f value of the nth coefficient. Okay. Right. So alpha is this one. Okay. Because we have a sequence, right? So we have a sequence of complex numbers, and so we are able to compute this lim sup. Okay. And we know lim sup of so from Cn we have right from this sequence of complex numbers, we have a sequence of positive numbers, right? We have a sequence of positive numbers, and as we know that for any sequence of real numbers, we always have a lim sup as well as lim inf, right? So this quantity must exist. And this quantity, because that our sequence is non-negative, so this lim sup can be any positive number or can be positive infinite. Okay? It can be infinite, right? Okay, so alpha can be all right, so let me make a remark here. Things okay, so alpha, so the lim sup, so we know okay, well, between 0 and the positive infinity. Okay, 0. Okay. All right. So it's very important to build your ability to find lim sup of a sequence of real numbers. Okay, that's why I want you to study the first section. Okay, I developed some techniques for you to compute the lim sup. Then the power series. Okay, the power series summation Cn. Okay, converges. All right, absolutely. If z minus z0 has magnitude less than 1 over alpha, okay, and diverge, right, and diverges if the difference between the distance between z and 0 is greater than 1 over alpha, right? But we don't know the divergence, our convergence property, if the distance between z and z0 is equal to 1 over alpha. We don't know. Okay? It's undetermined. We don't know that. So that is the, okay? So with this quantity alpha, we are able to know that when the in what kind of z the Power series converges. Okay. All right, and in here, okay, if alpha is 0, of course the inverse is infinity, right? So it means that for all z, the pulses will converge. So if alpha is 0, okay. But if alpha is past infinity, then 1 over this quantity is 0. Okay, it's 0. And so for all z other than z0, the pulses will diverge. Okay, it's equal to 0 if and only if the distance is 0 if and only if z equal to z0, right? But if z equal to z0, the power series of course converge to 0, no problem, right? Okay, so if alpha is infinity, then the power series will diverge, except at the center. Okay, so at the center. Right. So you know some interesting consequences once you know this theorem. Okay. Any questions? Okay. Now the number So we know 1 over alpha is an important number, right? So the number rho equal to 1 over alpha, okay, with alpha in the above theorem, okay, is called the radius. Okay, it's called the radius of convergence. So we call ROC, okay, of the power series. Okay. Okay, the ROC. Okay. So in terms of picture, let's see. So if we write a picture here, and the center is Z0, okay, and we find a disk, okay, and radius is equal to rho, which is 1 over alpha here. Okay. So now, in this disk, all the z in this disk, right? All the z in this disk give us give us a convergent series. But if Z is outside this open disk, then the power series will diverge. Okay? For those Z outside of this open disk. But for point on the circle, right? On the circle, the boundary of this disk, we don't know. Okay? We have to check point by point. Okay? So that is not specified in this theorem. Okay. Any questions? Okay, so with this theorem, we can state theorem 15.2.1 in the textbook. It says that every power series, all right, converges at right, converges at its center is 0. Okay. Second, if the power series converges, okay, at a point Z equal to Z1, which is not equal to Z0, then it converges absolutely, okay, for every Z closer to Z0 than Z1, i.e. for all Z has distance which from Z0, which is less than Z1 minus Z0. This is of course true. When we know that a power series converge at a point Z, all right, equal to Z1, then this point must be either on the circle, right, or inside the open disk, right? So let's draw the situation. This is Z0, and so now we have okay. So this is 0. So when we say we have a point Z1 which converge, right? When we put so that this series converge, then the only situation, so Z1 cannot be outside, cannot be in this area, right? In the outside of the cross disk, so cannot here. So Z1 is either on Z1 is here or possibly in here inside. Then, if it's in Z1, on the y, then if Z minus Z0 is less than this difference, then Z must be in the, then this implies that Z must be in the disk, open disk, right? So Z here or Z here, okay? So of course, it converges absolutely because that because the theorem states that. Okay. Now, if the power series diverges, okay, at a point Z equal to Z2, not equal to Z0, okay, then it diverges. So it diverges, okay, for all Z, okay, farther away from Z0, then Z2, i.e. Z minus Z0 is equal to then Z2 minus Z0. So if we know that a point Z diverge, right? So it diverges is possible is that Z2 may be on the circle. Our Z2 is here, okay? Z2 is outside of the cross disk. So there are only two possibilities. And so that so that if we have Z here or here, okay, so this Z must be outside the cross disk, and so that for all such Z, the series will diverge. Okay. All right. So second and third statement is are consequences from the theorem here. Okay. So the basic thing is that you have to grasp this theorem, the content of this system. This is the basic things we have, and then it is very important to know the ROC of a power series, the radius of convergence. Okay, and to find that, you have to find the lim-sup first, and take the inverse of alpha. Yeah. Okay, so let's just take a break. Okay. Okay. In Theorem 15.2.8, we use the root test to find the radius of convergence here. Okay. And sometimes it's not easy, right, to find the lim sup. Okay. So another way out is to use the ratio test. But to use the ratio test, you need to find the limit. Okay, so this is the theorem provided in the textbook. So suppose we have a power series. Okay, so we have power series with non-zero coefficients. If non-zero coefficient for all n greater than capital N, all right? All right, so suppose that we have a power series, okay, and its coefficients is non-zero, all right, for all index n greater than or equal to a capital N, all right? All right. Now assume that the limit alpha equal to n goes to infinity Cn plus 1 divided by Cn. Okay. So this is the reason why we require that the coefficient C7 are non-zero when little n is greater than some positive integer capital N. Right. So the limit exists. Right. Not just only lim sup, limit. Okay, so this is the stronger condition. Okay, and as we know that for any power series, this limit may not exist. Okay, it's not like this theorem. All right, you can always find the alpha by using the lim sup. So this always exists, but this one may not, all right? Okay. Then the power series, okay. The power series converges absolutely if z minus z0 is less than 1 over alpha, and diverges if z minus z0 is greater than 1 over alpha. Okay. So now, which means that this alpha is just the ROC. 1 over alpha is just the ROC of this power series. Okay? And this alpha would be the same as the alpha found by compute this lim sup. Okay? So they must be equal. Okay. Right. So this is another way to find the ROC. but not always not always successful. Okay, not always. Only for it's good only for some power series. Okay, only for some power series. So if this limit cannot exist, then you have to go back to the theorem to find the lim sup, all right, of this nth root of the absolute value of Cn. Okay, so you should use the root test instead of the ratio test. Okay. And there are quite a few examples in the lecture notes, as well as in the textbook, for which we have worked out and to show how to calculate the ROC of a power series. Okay. So now we will talk about functions given by power series. Okay. Now, so given Z0 and C given Z0 and in C and a sequence of complex numbers, okay? Right. We can define a complex function all right? So we can define a complex function f from D0 rho to C. Okay. As the function value is the sum of the power series. Okay. Where rho is equal to 1 over rho is equal to the lim sup of the square root of the absolute value of Cn. Okay. So given the sequence, we always find out the rho here, right? And so we can find this, define the function. And this function is well defined because theorem 15.2.8 here. Okay. So for every z, for every point in this open disk, this series converges. Okay, absolutely. So we can have this function f is well defined. by Theorem 15.8. Okay, it's well defined. And we say that the complex function f of z is given by a power series about the point z equal to z0. Okay. Right. So in this section, we'll talk about such functions. Okay. All right, so Fz all right, so Fz is a complex function given open disk given by a power series. Okay. Right. So now we consider a function, a complex function, all right, defined on this open disk given by a power series. Okay, and with 1 over rho is equal to the lim sup of the nth root of the absolute value of the nth coefficient. Okay. Then f of z is analytical. All right. So f of z is analytical on the open disk, and its derivative. Okay, f prime z can also be given by a power series about the point z equal to z0. So, okay, about the point z equal to z0. Okay. With the same with the ROC, with the ROC rho such that, okay, with the same ROC rho. Right, and which is obtained by directly differentiation, right? Differentiating each term of the series. Okay, so i.e. F prime Z is just equal to n Cn minus 1. Okay. So it's very nice because if a function is defined by a power series about the point z0, right, and with RO0 such that the inverse of rho is the lim sup, okay, of the nth root of the absolute value of the coefficient Cn, okay. Then such a function is analytic, okay, it's analytic, right? On it's defined in domain, which is just the open disk, right? And its derivative, of course, because it's analytical, so its derivative exists. And this derivative actually can be obtained directly by differentiating each term of this power series. So the differentiation of this term will be this one. Okay, and starting from 1 here. So the derivative of z, all right, is equal to the sum of the derivative of these terms, so that the differential operator and the infinite sum can exchange the order, right? Which means that we can exchange the order. So when we take the derivative here, okay, the derivative here, but we can exchange them. We can exchange them. Right. So the theorem says that it's exchangeable. Okay, and this power series has the same what? Has the same radius of coefficients. Okay, have the same radius of coefficients. Okay. Okay. So the reason I read here to show you that if we compute the lim sup, okay, so this is the okay. If we compute the lim sup here of the coefficient of this power series, right? And this is actually the limit, because this is the product, right? So this is the lim sup. So this can be times, okay? So it's this one. But the sequence of this one converged, right? So the nth root of n has limit which is equal to 1. So that by our theorem, and this is equal to 1, so this is lim sup. Okay, and which theorem we apply? Well, it's theorem. So by Theorem 15.1.h. Okay. Right. So in this theorem, that if we want to compute the product of the instance of the product of sequences here, like this one, and we know that one of the factor has limit here. Okay, not just only limit, just has a limit. Then this limit, the limit of this product is equal to the product of the limit of this term of this factor times the limit of the other factor here. So you can see that they have the same limit. So that's why they have the same radius of convergence. Okay? So this power series and this power series has the same radius of convergence. Okay? It's not a surprising result. Okay, but so here. And once this is the power series, again, it's analytical, right? It's analytical. And so function defined by a power series is analytical. And by our study in chapter 14, that this function has any nth order derivatives. Okay, but it gives us the detail. It gives us how to find derivatives. So if you want to find the second derivative, well, you do the differentiation for this term again. Okay, so it's very easy to find the derivative if a function is defined by power series. Any questions? Any questions? All right. So if no questions, then we move forward. All right, so a direct consequence of the previous theorem is as follows. Okay, which is a theorem in the textbook. It's called the continuity. Right. So if a complex function f of z is defined, is given, or I should say, is given by a power series. Is given by a power series about the point z equal to z0 with ROC, rho is greater than 0. Then f of z is continuous on the open disk d z0 and the rho. Okay. Of course, f of z is analytical, so that f of z is differentiable at every point in the open disk. So of course it is continuous. Right. So this is an easy consequences. I just and another theorem given in the textbook is about the uniqueness of power series expansion. Okay. If a complex function f of z is given by a power series about the point z equal to z0, then the given power series, okay, is unique. Okay, and this is again a direct consequence of this theorem too. Okay, the reason is here. I think I give a very quick proof here. Suppose that the f of z can be represented and also right about the same point, right? And right. So if this is true, and we know the answer derivative. Okay, so let's k. So the k's derivative is equal to n to k. Okay, and the n minus 1, n minus k plus 1. Oh. 0. Okay. Maybe I say. So f is 0. Oh no. F is z0. Okay, is equal to c0 b0, right? If we evaluate the value at z0, so it is constant. Okay, I'm sorry, it's not 0, it's constant. Okay, so sorry, it's a constant. All right, it's 0. And for all k greater than or equal to 1, the k's derivative of z is equal to n from k infinity. So it's n minus 1, n minus k plus 1. Yeah, 1. Okay, and the c n z minus z0 and n minus k. All right. And this is also equal to summation n equal to k infinity n minus 1 minus k plus 1 and the Bn z minus z0 n minus k. Okay, and so when we evaluate the case derivative at z0, then we have that this is n minus 1 c. So when k 0, yep. So k okay, so it's equal to 1. Good. Is that correct? Yeah. So we have k factorial, yes, good, and the ck, right, equal to k factorial and bk. Okay, so they must be equal, right? So this implies that ck equal to bk for all k greater than or equal to 1. Right, so they must be the same power series, right? Is that okay? So we assume that we have two power series expansion formula for the same complex function. So suppose that this function is given by power series, and suppose that this two power series we have this one, that one. Okay, they give the same function. So first, when we evaluate f at z0, then of course we find c0 is equal to b0. So they have the same constant term. And then for all k greater than or equal to 1, when we compute to the case derivative of f of z, by the theorem here, we can do it term-wise, right? So with this term-wise, we get this one, okay? When we do the case derivative. With this one, the term-wise, the case derivative of this one is this one. Okay. And then we evaluate the case derivative at z0, okay? All right, except n equal to k. When n greater than k, this factor is 0, right? This factor is 0. So the value will be k infinity k factorial times c sub k, and with that, the value is k factorial times b sub k, and they must be equal because this is the function f is definite. So we have this one, okay, and cancel the k factorial, you get this equality, okay. Any questions? Okay. And the theorem 15.3.3 in the textbook has the same content as that in Theorem 15.3.8 there. Okay. And the term-wise integration all right, now the power series summation n from 0 to infinity Cn n plus 1 z minus z0 n plus 1 obtained by term-wise integration. All right, so this power series is obtained by term-wise integration. Okay. So of course this function is different from the original one, right? We used this power series and to do the term-wise integration. So this is a new power series. So this new power series of the original power series okay. So this power series has the same ROC as the original power series. Okay. Right, and this theorem has a usage. If you want to find the ROC of this original power series, and by using the root test, suppose you can't find the ROC by using the ratio test. Suppose you can't. Okay, so you have to evaluate the name sup of the nth root of the absolute value of the nth coefficient. Suppose that. This is one way you can do. Maybe it's hard. Then you can go to look for the ROC of this power series because they have the same ROC. And it may be this one, right? If you use the root test, okay, this power series, the coefficient here, right, may be easier to deal with. Okay, so it provides another usage. Okay, if your purpose is to find the ROC of this original power series. Okay. Now, in the previous section, right, we consider function defined by power series, right? So we can use power series to define the complex function. Now, here, we start with an analytic function, okay? We start with an analytic function. And we want to know the power series expansion of analytic function. So okay, so now a complex function f of z defined, right, in an open set omega is called representable, okay, by power series. By power series in omega if to every open disk D0 are contained in omega, there correspond. So there corresponds a power series n from 0 to infinity Cn z minus 0 as power about z equal to d0, which converges absolutely, okay, to f of z in the open disk. Okay? So it's called representable by power series. So suppose that we have a complex function defined on an open disk. Okay, so omega is an open set. Sorry. Okay, so open set, and f is defined in this open set. F is defined in this open set, and we say this complex function f is representable by power series in omega. If we can find an open disk for every open disk in this open set, okay, so here, so let's specify. All right, so okay, so we have a D Z0 R. So now this open disk is in omega. Now it's in omega, all right? So the whole open disk is in omega. Then we can find a power series, okay, about the center of this open disk. Okay, a power series about the center of this open disk, which converge to Fz, okay, for all points in this one. All right, so that means that in this open disk, the complex function can be given by a power series. Can be given by a power series here, okay, and every point, all right, in the open disk, right, the series sum goes to f of z. Okay. So it's called representable by power series. Okay. So in here, the power series is here, right? And we find the power series. So all right, the f of z, okay, representable by here. Now, if we find another open disk, okay, so this is z prime and r prime here. Okay, and so we have d c 0, okay, 0 prime r prime inside here. Then in this, right, the f of z is equal to, maybe it's Bn. Okay, so that the Fz is given by another power series, and the coefficient Bm may be different from Cn. Okay, may be different from Cn. Okay, and of course z sub 0 prime is different because they are these two centers are different because they are in different locations. Okay. Okay. So analytic function is representable by power series. We mean this is situation. All right, and the question is, so you can see if a complex function is representable by power series, right? So for example here, now, so you can see this function f of z should be analytical, right? Because power series, as we know by theorem 15.3.8, this function should be analytical. So it is analytical in every point in this open disk. Okay, and because this is true for every point, because for every point in the open set, we can always find a neighborhood, right? We can always find a neighborhood. So this is not, we can find a neighborhood. And in this neighborhood, we know the function f of z is given by a power series. Okay, so a consequence that an analytic complex function which is represented by power series must be analytical. This is the consequence, right? So now since a complex function given by a power series is analytical. All right? In its defining domain. Okay. All right. Any complex function all right, which is representable by power series on an open set. So any convex function on an open set which is representable by power must be analytical on omega. Right? And the theorem 15.4.8 gives us the converse. Says that an analytic function f of z defined in an open set omega, it's representable by power series in omega. And that is to each open disk, okay, the Z0 and the R in omega, okay, there corresponds a power series, okay, correspond power series expansion of f of z about z equal to z0. So this power series expansion is here. Okay. The coefficient is determined by okay. So now the coefficient can be determined. Okay? So if f of z is an analytic function, because we know analytic function is a necessary condition already, right? By our discussion, right? If a function which is representable by power series in an open set must be analytical in the open set. Okay, right. So and for any analytic function, we show, right, it is also sufficient condition. Okay. All right, and for any open disk in omega like this one, then how can we find the coefficient? The coefficient actually is determined by the derivatives, okay, of the analytic function at the center of the power series, okay, Z0, okay, and which is called the Taylor series expansion, right, as we know. So which is just the Taylor series expansion of f of z about z equal to d0. Okay. Okay. So we can find the coefficient here. Okay. Okay. So I stop here.